Thank you, Yakov, for the introduction, and really want to take the chance to thank both of the organizers for putting together such a wonderful program. It was a true delight to hear many of the interesting talks before me. And of course, I'm also honored to be the last or the -1 or +1 presenter in this workshop. So this is a joint project with Rong and Kfir. I believe both of them are in the audience. So if you have any questions, you can, of course, directly ask me, but also feel free to type your question in the chat. And I should apologize that I sent a hello message to my co-author thinking that it's a private message, but it's actually sent to everybody. So forgive me for that. So, you know, Dirk has already sort of set the stage for many concepts that I'll be talking about in this paper. You know, we're going to be thinking about an auction setting. And what happens in many auction settings is that after the auction is carried out, the identity of the winning bidder and the actual payment will be disclosed to the public. This happens, for example, for public procurement auctions, where there's oftentimes a open online database where anybody can search for the past records. It also happens for some private auctions because private auction houses have the incentive to advertise their ability to achieve high sales prices. In some of these situations, the winner identity may not be disclosed by the auction house, but oftentimes, such as in art auctions, the identity of the winner will somehow get its way to the media. So there are certain professional websites, such as the ones listed here, that make reports on past auction outcomes. Now, of course, this kind of disclosure facilitates the transparency of the auction and can prevent potential corruption. But at the same time, it also leads to privacy concerns for potential bidders who might be worried that in the event they win the auction, the information revealed about their willingness to pay may be used against them in the future. So this could happen if the same bidder plans to engage in future auctions of similar objects. It could also happen if after winning the current auction, the bidder is going to engage in some aftermarket transactions, such as resale or subcontracting. And in those aftermarket transactions, you know, information leakage about the bidder's willingness to pay may weaken his or her bargaining position. So the questions that we are going to pursue in this project is the following. We're going to ask which auction format minimizes the winner's loss of privacy, or more formally, the loss of privacy regarding the winner's type incurred through observing the identity and the payment. But we're going to constrain our problem to auctions that already achieve a primary objective that the seller may have, which could be efficiency or revenue maximization. I'm going to elaborate a bit more on this objective function in a couple of slides. So without further ado, let me just jump into the model. Of course, as you can already imagine, there is a large literature related to this work. I'm going to talk about the connection between our work to the existing literature after I present the model. So we have a fairly standard independent private value auction setting. There is a single seller who owns 1 unit of good, and we're going to normalize the seller's reservation value at 0. In the auction, there are going to be n risk neutral buyers whose values are denoted theta 1 through theta n, and these value types are ID drawn from a common value distribution F. And as a standard, we're going to assume that the buyers will have quasi-linear preferences. The common distribution F will be assumed to have an interval support and the density that satisfies the monotone hazard rate. So specifically, the inverse hazard rate that I'm highlighting on the slide should be decreasing in the type. This is slightly stronger than the usual regularity assumption, which requires the virtual value, which is x minus the inverse hazard rate, to be increasing in the type. But monotone hazard rate is still satisfied by a lot of distributions, in particular, any distribution with a log concave density. For the ease of notation, I'm going to go directly to the direct mechanism setup. In this sense, I'm invoking a version of the revelation principle, which will be clear holds for our problem. So in the direct mechanism M, there are going to be two functions, Q and P, specifying the allocation as well as the payment. The allocation function Q is standard. It maps the type profile to the probabilities of allocating the object to each of the buyers, subject to the feasibility constraints. The payment rule is a little slightly more non-standard because we're going to allow randomized payments. So you can notice that the payment function here maps a profile of types to a distribution of vectors of payments. By allowing for randomization, we're essentially already thinking about the question of whether randomized payments can help reducing the information loss, information revealed about the winner type. We're going to throughout assume that the buyers can walk away. That is, we impose the interim individual rationality constraints, which requires the expected payoff of every buyer type to be non-negative. So let me say a bit more about the designer objective in our model. For most of this talk, I'm going to assume that the seller is a benevolent designer who seeks to maximize total welfare. And as we know, the way to maximize total welfare is to allocate the good efficiently to the buyer who has the highest highest type. So QI, this allocation function, should be 1 if and only if the type, the willingness to pay of buyer I is the highest among all the buyers. The results that I'm going to present do generalize to any objective function that is a linear combination of welfare and revenue maximization, but I'm going to discuss that extension later on in due course. We're also going to make a fairly restrictive assumption, which is a restriction to dominant strategy mechanisms. Now, there are various ways to justify this assumption. One common way to justify it is that dominant strategy mechanisms eliminates any concerns the seller may have about the buyer's information structure or their strategic reasoning. But it also just simplifies our problem dramatically because combining the efficiency assumption and the dominant strategy assumption, we can basically pin down both the allocation and the expected payments at any type profile. Okay, now notice here that the distinction from the standard setup is that in the standard auction setup, the payment is generally assumed to be deterministic. So then everything that the auctioneer can do is pinned down by efficiency and dominant strategy. Here, however, we're allowing for randomized payments. So dominant strategy incentive compatibility translates into the constraint that I'm highlighting in red, which says that at any type profile theta, the expected payment of the highest type is equal to the second highest type. Okay. And for everybody who doesn't, whose type is not the highest, the payment is of course 0. Notice that at least in terms of expected payments for each type profile, this is the same as the standard second price auction. And again, the difference is that we allow potential randomization. So as described, the seller in our model will be choosing an auction format within the class of efficient and dominant strategy auctions. But we also want to introduce a privacy measure. So the seller's objective in our model is going to have a flavor of a lexicographic preference. Specifically, among all efficient dominant strategy mechanisms, the seller will seek to find the stochastic payment rule satisfying this red constraint for dominant strategy. He wants to find such a payment rule that would minimize the privacy loss of the winner type that is incurred through disclosing the payment. And on the next slide, I'm going to formally define what we mean by privacy loss. But any questions so far?
Yes, are they risk averse, these bidder?
Risk neutral.
Risk neutral, yeah. So what prevents me from taking a standard auction and just adding a huge noise to the payment that will make it uninformative about the true payment, like a huge noise with 0 expectation?
Excellent question. So that's, well, that will be in the first 2 results that I'll show. So you're already thinking a bit ahead, but you're absolutely, so in short, you're absolutely right that without further constraints, that's something the seller can do.
Okay.
And we'll see what kind of constraints. So for example, at this stage, we're already constraining to positive payments. So we need to be at least a bit careful in terms of adding noise.
So I guess you're going to define what formal the privacy loss is, right?
Exactly. It's coming on the next slide. Okay, so we're going to measure the loss of privacy as using an information theory criteria. And we're going to measure this loss as the mutual information between the winner type and the realized payments in the auction. Just to walk you through this idea a little more slowly, given any stochastic payment function P, we can denote by W, which is the maximum of the buyer types. And because of efficiency, this will be the random variable of the winner type in the auction. Mm-hmm. On the other hand, I'll denote by capital P the random variable of the winner payments. Now notice that even though I write it as a sum, it's actually only the winner's payment because all losers pay 0. So this stochastic payment function P that the auctioneer can design will determine the joint distribution between these 2 random variables, the winner type and the realized payments. And I'm going to call this joint distribution lambda subscript WP. This joint distribution will also induce 2 marginal distributions, which are the distributions of the winner type alone, as well as the distribution of the payment alone. So with this notation, we're going to calculate the loss of privacy as the mutual information between the 2 random variables, capital W and capital P. as many of you are probably familiar, there are multiple ways to define the mutual information. One way to define it is through the first equality here, which says that the mutual information is the K-out divergence between the joint distribution and the product of the marginal distributions. So the O times here will always denote a product of two distributions. An alternative way of thinking about it, which is perhaps economically more intuitive, is through the second equality. And the second equality says that the mutual information is also equal to the expected K-out divergence from the posterior belief of winner type to the prior belief. So in this formula that I'm highlighting, lambda of W given P is the posterior distribution of the winner type conditional on observing the payment. So inside the expectation, we're measuring the distance between this posterior belief and the prior belief using K-out divergence as the measure. And then we take the expectation over different possible realizations of the payments. This will give us an average measure of how much belief will change upon observing the payments. We think of this mutual information measure as a reduced form measure of how much can be learned about the winner type from seeing the actual payments. As I'll discuss in the literature review, this approach contrasts with many existing papers that explicitly model future interactions between the winning bidder and some third party. In our project, however, we're not going to explicitly model those future interactions. And in fact, we think that in many situations, there is uncertainty about how this information will be used by a third party in future interactions. So let me just walk you through an example to illustrate.
Xiaosheng, can I ask a quick clarifying question? So is it fine to think about it this way, that basically this is where your model starts? We can forget about everything you said earlier. And basically what we have is two random variables, W with the marginal distribution, P with the condition that when W is realized, there is a certain expectation of P that we must maintain. And we just want to minimize this KL divergence among these two random variables. Is it fine to think about it this way in some sense?
That's almost true. And in fact, that's also that idea is gonna appear in our proof strategy that I'll later describe for one of the main results. But one thing I should emphasize is that there are more random variables than W and P. So sort of part of the constraints that you're referring to regarding the expectation is about the second highest type, which is not a function of W. So in the background, there are also these other correlated random variables.
I see. And I meant it as a compliment, because what I'm saying is you solve an interesting mathematical problem. What you presented so far is just one application. There could be other applications of this mathematical, apparatus, basically.
That would be great. That's I really appreciate this comment. We will, in fact, present a tactical result in the spirit of what you just described. But if any of you has other applications in mind, that would be fantastic. Thank you.
Sorry, Piotr's question just reminds me. So you calculate the loss of privacy in this way. I could simply ask that I want to minimize the conditional variance of the first order statistic, conditional on the observed prices.
Mm-hmm.
Would that give me a different answer, or?
Good. This is jumping a bit ahead as well. For some of the results, it doesn't change, but for some other results, if we change the divergence measure here to something else, then the results may not hold. At least our as you will see, one of our results crucially relies on some features of mutual information, which a priori we didn't expect either.
Mm-hmm. Great.
Okay, so an example is the simplest example one can think of. There are just two buyers whose types theta1, theta2 are both uniformly drawn from the unit 0, 1 interval. I'm going to just let the seller uses the standard second price auction with deterministic payments. Then in this case, the two random variables of interest, W is the maximum of these two types, and the price is the minimum of these two types. So their joint distribution is the uniform distribution on this blue triangle in the figure. W is on the horizontal axis, and P is on the vertical axis. Now, having calculated this joint distribution, we can also get their marginal distributions. W turns out to have density 2 times little w. The random variable P has density 2 times 1 minus P. And plugging these densities into the KL divergence formula, we can compute the mutual information between these two random variables. So let me briefly talk about the related literature. There is several strands of large literatures that this work connects to, but I'm only listing a few here, and we very, very much welcome suggestions you may have. So Piotr has a paper that studies a problem where the seller sells an object to multiple buyers, the winner of whom then engages in an aftermarket. In his model, the seller is going to design an allocation rule joint with a disclosure rule, and the payoff of the seller depends both on the winner type as well as the posterior belief about the winner type given the disclosure rule. So the main difference of our paper is that we take this lexicographic approach, and in the sense that we fixed the allocation rule to be something that is already very desirable, whether it be the efficient rule or the revenue maximizing rule. And in addition to that, we also require the seller to disclose the payment, mostly for practical reasons. And because the seller is already disclosing the payment, disclosing more information can obviously only hurt privacy. So in our problem, there's not really a design of the disclosure rule. Dirk and Johannes, as well as many other papers, study a problem where there is repeated interactions, where information gleaned in prior interactions can be used in future periods. As I discussed, in our project, we're not really explicitly modeling future interactions, which are potentially unknown. And then, of course, speaking about privacy, one cannot not mention the differential privacy approach that is very popular in the computer science literature. In our project, we're adopting a Bayesian approach that is based on how the posterior belief differs from the prior belief. We use this to measure privacy loss, and in this framework, we can study whether and how a Bayesian optimal or efficient auction can be improved. Whereas in the differential privacy literature, because of the way differential privacy is defined, it requires randomizing over allocations, and therefore one cannot get an efficient allocation to begin with, a fully efficient allocation to begin with. Okay, so now let me tell you about our results. The first result is essentially in the spirit of Aaron's question earlier, which is that without further constraints on this problem, the first best of full privacy can be almost achieved. More formally, the proposition says that given any privacy level epsilon, there exists an efficient dominant strategy auction that achieves privacy loss less than epsilon. And the idea is exactly as Aaron foresaw, which is to appropriately add noise to the payment. But more specifically, what we can do is to ask any winning buyer to make a randomized payment between some very large amount, capital K, and a low amount of 0. From the outside observer's perspective, when he or she observes a payment of 0, the belief about winner type doesn't change much because 0 occurs with conditional probability close to 1 given any type profile. On the other hand, if the outside observer sees a payment of capital K, this does affect the belief. But because this large payment only occurs with small probability, this event of seeing the large payment is very unlikely.
5 minutes.
Okay, because of this, the expected K-out divergence can be made arbitrarily small if we let K go to infinity. Now, naturally, we might want to, in light of the previous result, we might want to impose an upper bound on the realized payment. It turns out that in this case, the previous construction of randomizing between 0 and the upper bound on payment is the privacy optimal thing to do. And the basic idea here is that any payment between 0 and this upper bound can be replaced with a randomized payment supported on these extremes that preserves the mean. And in this way, we're garbling the payment in a way that doesn't depend on the winner type, which reduces the information revealed. More realistically, we can consider an alternative form of upper bound on payment in the form of ex post individual rationality. And this will be the setting where our mean result is derived for. So ex post individual rationality requires the payment to be supported between 0 and the highest winner type. So this is going to rule out the previous construction of randomizing between 0 and some high payment. But perhaps surprisingly, this theorem that we show establishes that under the ex post individual rationality constraint, no randomization can help reducing privacy loss relative to the standard second price auction. So because I'm a little short on time, let me quickly tell you how we prove this result. So recall that we want to minimize the K-out divergence between the joint distribution and the product of the marginal distributions. Our analysis is going to proceed in 2 steps. In the first step, as Piotr kind of suggested, we're going to fix the marginal distribution of the payments. Notice that the marginal distribution of the winner type is fixed by the common value distribution. In the first step, we're also going to fix lambda p and characterize the optimal lambda WP, the joint distribution that minimizes mutual information. And in the second step, we're going to optimize over this marginal distribution of payments. So given 2 marginal distributions, one for the winner type and one for payment, we're going to define this set, capital lambda, to be the set of all joint distributions with these marginals and satisfying additional constraints that the payment cannot exceed the winner type. That's coming from the ex post IR constraints. Now this essentially says that W is going to stochastically dominate P. So this set of joint distribution is non-empty if and only if the 2 CDFs are ranked everywhere. And here is our main technical theorem characterizing the minimum K-out divergence achieved by some joint distribution with these marginals. So the exact formula doesn't really matter, but what I just want to draw your attention to is the fact that the infimum of the mutual information can be expressed as a certain integral that depends on the CDF of the marginals, and that specifically depends on the difference between the CDF of the marginals. So there are two limit cases that one can consider to understand this infimum. One case is when the two CDFs are the same, in which case the price has to be always equal to the winner type. In this case, there's only one joint distribution with these marginals, and this joint distribution is not absolutely continuous. So that would lead to infinite K-out divergence. And on the right-hand side, we see that because 1/0 is infinity, we get an infinite integral on the right-hand side. One can also understand this formula in the other limit case, where the support of the payments are uniformly smaller than the support of winner type. But what's more important for our purpose with regard to the second price auction is this characterization of the optimizing joint distribution that's highlighted in blue. And it says that the optimal joint distribution has a product density, except that it's conditional on the event that the price is less than or equal to the winner type. Yaakov, how much time do I have? 1
minute.
Okay, so I'm going to skip talking about discussing why product density is optimal and go straight to the connection to the second price auction. So recall the example of two buyers uniform types. Then these two random variables are going to be uniformly distributed on this triangle. And this is exactly a density that has the product form. It's the uniform distribution on the entire square conditioned on the triangle. And more generally, the second price auction has the property that the highest and second highest type has a joint density with the product form. And so what this tells us is that conditional on the distribution of the payment being the same as under the second price auction, then the joint distribution achieved under the second price auction would achieve this mutual information lower bound established in the theorem. And then in the remaining step, we argue that any other ex ante payment distribution will lead to a higher mutual information upper bound. And this is the step where we use the dominant strategy assumption because this gives us a lower bound on the dispersion of the payment distribution. I'll conclude with some open questions and hope to hear your thoughts.